We're a little bit behind, so I'm gonna focus on picking up the pace a bit. So rotation, and we started talking about rotation last time, and we got to the stage where we talked about how you can convert from angular to linear and linear to angular. There's equivalencies, and we'll actually learn a bit more about actual rotation. So what we're going to do today is we're going to talk about angular displacement, angular velocity and acceleration, angular quantities and translational quantities, and we can move backwards and forwards between the two of them. We're going to introduce the idea of angular force, which is like torque, and then angular mass, which is like moment of inertia, and then we'll talk about angular kinetic energy, which is like rotational kinetic energy, and then we'll put it all together in a rolling fashion, and we'll talk about rolling motion. So there's a fair bit that's quite testable in what we do today. As I said last time, if you were a space alien, you wouldn't know anything about degrees, but you would know about radians. It just comes out of the geometry of the situation. If I have a radius and I walk a radius's length around the circumference of a circle, then I define an angle, and we simply call that angle 1 radian. So we say, consider a point P moving on a circle. The distance along the circumference is S. The radius of the circle is R. The angle in radians is theta. Theta is just a number. And mathematically, we're going to say that theta in radians is equal to S over R. Okay, if I want to talk about displacements, I have a starting address, which is a certain angle, let's say theta I, and I have an ending address, let's say theta S, and when I subtract one of those from the other, I get my angular displacement, just like we had for linear displacement. I can get an angular speed, and for angular speed we talk about omega. Omega, it's called omega, it's curly W if you like. It means angular speed, it's in radians per second. And omega equals the limit as the little bit of time goes to 0 of, man, this is a bit of a mess, isn't it? It's going to be delta theta by delta t, which equals d theta by dt. And angular acceleration, which is alpha, and this is as delta omega over delta t equals d omega by dt. And if you just think in terms of linear terms, and then you just substitute in, every time you see an x, you put a theta, every time you see a v, you put an omega, and every time you see an a, you put an alpha. It all works just the same. So get used to the terminology. Don't let Greek letters corner you. Don't let strange sounding letters corner you. I put a little video on the website which has the pronunciation of Greek letters. It's part of comes with the territory. Engineers know a fair number of Greek letters and know how to pronounce them, so just jump on that. Don't let that put you to one side. Every point of a rotating object has the same angular displacement, angular speed, and angular acceleration. That's really why we're here. If I have a rotating wheel and I want to compare the physicality of 5 points at different radiuses, they have, well, in time they travel by different distances around. They travel at different velocities, or different speeds I should say, because they're traveling by different distances in the same amount of time. And if it's speeding up or slowing down, they have different tangential accelerations. So tangentially, this is a mess. But in terms of angular things, they all start off at the same angular address, and they all end at the same angular address. They all have the same angular displacement. They all have the same angular velocity at any instant, and they all have the same angular acceleration at any instant. So it takes this complicated, radially changing field of information and brings it down to 3 basic numbers again. So it's really useful. Remember, everything in your physics book keeps being in your physics book because it's proved itself to be really valuable. There's nothing in there just to fill the thing up. So you are more powerful with each new thing you learn. If you try and do, like what I would tend to do is, because I'd mastered something, I would try and adopt it to the new thing. Do I really need this? I can do it the old way. And what experience showed me was, as time passed, I would find that, man, if I only knew the new way, I would be able to do this much easier. So just embrace the new stuff. It's not a new test, it's a new opportunity. So here's my one-page takeaway. So your linear stuff and your angular stuff are all related, and we can just translate our equations across. And the kinematic equations are all basically the same. I don't learn the new kinematic equations. I know the old ones, and I just translate. You know, it's like. But I'm not going to try and solve these things using tangential information. I'm going to use angular information. So a student runs 40 meters around a circular track. It's 50 meters radius. Can you tell me, please, what is the angular displacement? So she starts off here. You can call that 0 radians. She ends up there. What is delta theta? Oh, excuse me. So remember your definition of your angle in radians, and then just you're looking for we said that equals 0, so and we're back, and let's just stop that there and see what people are saying. People are saying basically B. Let's see where that comes from. We say, well, okay, my displacement is equal to my final position minus my initial position. I don't know my final position, but I know I said at the beginning that my initial position was 0 radians. So what about this final position? Well, my final position is going to be the S over the R. That's how I get my angle in radians, minus 0, which equals my S is going to be 40 over my R is 50, minus 0. So delta theta is equal to 0.8 radians. And might as well get started on this, because I'm going in a counterclockwise direction. I'm going to call it positive. Okay, just I got to pick one or the other, and tradition is that counterclockwise is positive. So no big deal that it's positive. Okay, not so bad. Point in a rigid cylinder has an angular velocity of that at a time given by that, and the cylinder has an angular acceleration of that. What is the point's angular velocity at that? So that's a classic kinematics equation. Let's have a look. Can you have a go at that, please? So we're back. Let's have a look at this. Let's stop this and have a quick look. What do people say? Solidly A. Let's see where that comes from. So we did our diagram, and basically I was a bit careful with my diagram. I didn't pick necessarily the horizontal line, but I picked a line that was my starting point, and I put down my information. I said that my initial velocity was that, and my time was that. And then if you notice, I drew my angular acceleration, and I drew it wrong way. I didn't pay attention to the sign, so I just put it as a positive pointing arrow. And then I realized, no, it's a negative pointing acceleration, so I reversed my diagram because that matters. And then what I did was I put in my final position. And so traditionally with these things, I drew my diagram and then I make my list. And my list in this case would be omega I is equal to +3 radians per second. And my t initial, if you like, would equal 2 seconds. And then my alpha, my acceleration, is -5 radians per second squared. And then my omega f is what I want, and my tf is equal to 6 seconds. And I can actually say my delta t is equal to t final minus t initial, which equals 6 minus 2. I'm doing it in my head, I'm sorry. Which equals 4 seconds. And that's the catch that we tend to put in. We don't start you when the clock's 0. We start you at some other time. And we did that when we did the linear stuff. So what equation comes to mind now? You know, for me, I'm very familiar with my linear expression, so I'll even cheat sometimes, and I'll put down VI, and I'll put down A, and then I'll put down VF. Oh, I know what this is. I'm going to say VF is equal to VI plus A delta T, and that translates into omega F is equal to omega I plus alpha times delta T. So omega F is equal to, what was my omega I is +3 added to, what is my alpha -5, and then what is my t? My t is not 6 because it's my duration, it's my time interval, which is 4. So omega F is equal to +3 added to -20, which equals -17 radians per second. So there's my answer. Let me ask you a question. Initially, when I have a positive omega and a negative alpha, am I speeding up or slowing down my rotation? What am I doing? I'm slowing down, aren't I? Because when your acceleration is in one direction, your velocity is in the other, you're slowing down. And then later on, when I got a negative velocity and a negative acceleration, am I speeding up or slowing down? Speeding up. So what happened was this thing basically went like this. It went like that, stopped, and now it's going backwards like that. Yeah. So that's the path. And we've been here before. We've seen this before. Okay. So expect something on kinematics. And then what about if we want to go backwards and forwards between the translational or the angular or the rotational? Sometimes the two terms tend to be used, angular or rotational, and the linear, or if you like, the tangential information. You know, what's the relationship? And it's a beautiful symmetry. We already know, because we just defined it that way, that theta is equal to S over R. We defined that. Agreed? Now rearrange it. So S, which is my tangential displacement, if you like. It's a distance along the arc. S is equal to angular. We put the angular bit down, we put an R at the end of it. Angular. And it's the same pattern for all of these things. My tangential velocity is equal to omega R. And my tangential acceleration is equal to alpha R. So if you just remember that pattern, if you remember this, you can always recreate this. But if you remember this pattern that the R is always at the end, you can always go backwards and forwards between the two of them. As you go further and further away from the turning axis, whatever you're considering, be it tangential velocity or tangential acceleration, becomes linearly greater to keep up. So if you ever played that game when you were a kid where you all join hands and you're running along the playground, and then one kid or the other at either end, they're kind of playing chicken, and one of them stops, and everybody, if you're running like this, and then the guy here stops, you get a whiplash effect, and depending upon how many kids there are in line, this guy at the end gets just creamed because they are further and further away. And the more kids you get to join in, the harder it is for the people on the end. because they're going to go faster and faster. So just remember that relationship. And we learned before that AC is equal to v squared over r. That was our centripetal acceleration. Well, okay. I can do a angular equivalent. So AC is equal to not v squared, but omega r squared over r, which equals omega squared r. So we get that relationship from it. And I don't learn that. I know that, and I can always get to it. Cool. So we can go backwards and forwards. So that means I can give you stuff in tangential terms and expect you to get the angular stuff and then do something with it. Or I can give you angular stuff and expect you to get the tangential stuff from it. A point that is 5 meters from a turning axis on a rigid cylinder has an angular velocity of 3 radians per second. What is its tangential speed? So here's my point. It is 5 meters from my turning axis. It has a angular velocity. I do my angular stuff as like a curly arrow. Omega is equal to 3 radians per second. And then what is my tangential speed? I'm going to draw my tangential speed as a VT. So I simply say, okay, well, in that case then angular. VT equals omega r. Angular as an r at the end, so angular, put the r at the end. So then I say, well, I want VT, so this is not so bad. So VT is equal to 3 times 5, which equals plus 15 meters per second. So there we have it. Plus 15 meters per second. Not so bad. Rigid cylinder spins about a turning axis that passes through its center. A point located 3 meters from the turning axis has a tangential speed of that. What is the tangential speed of a point that is located 4 meters from the turning axis? So I want you, first of all, I want you to draw me a diagram. Let's pause and let's just draw me a diagram, and then we'll come back together. So let's do this diagram. So rigid cylinder, basically it's like a wagon wheel or a compact disc, all that thing. The outside and the inside are all stuck together, so you can't leave either one behind. And then we have a situation like this, and we say, okay, rigid disc spins, passing through the center. So there's my axis of rotation. Point is located 3 meters, so we're going to do 3 meters. So this is 3 meters. I'm going to say that that is a thing of 6 meters per second. And then this is 4 meters. And I want to know that guy. So that's 4 meters. So there's my 4 meters. My 3 meters and my 4 meters. And I'm kind of giving the game away already, because if you...
Is the entire radius 4 meters from...
Well, I've just drawn a diagram with 2 points on it. So that's 3 meters from the turning axis to that point. And it's 4 meters from the turning axis to that point. I drew it as a circle just to remind myself it's a circular thing. So somewhere I've got to find an equation which has, equal things on equal sides. So I need some consistency. And my tangential velocities are not the same, and my radii are not the same. So that's not going to do it for me. So what physical thing is the same for all points on a rigid cylinder? The angular velocity, and this is moving, so angular velocity. So I say, omega is constant. So I can say, if you like, omega of the left is equal to omega of the right. I'm running out of terminology. I'm saying this left-hand point and the right-hand point. And so I can say, well, what does omega equal? Angular Vt over r. So then that means V tangential on the left over R on the left is equal to V tangential on the right over R on the right. Just talking about those 2 points again.
It's confusing, switching between the W's and the V's.
But you just got to get used to it, because it's like they mean different things. So you're not switching, you're actually talking about 2 different things. They might both be velocities, but they're different things. So VT we know, VT on the left is going to be 6, and the R on the left is going to be 3. and this equals Vt on the right, well, that's what I'll find, over 4. So Vt is equal to, the rest is sums. 6 times 4 over 3. Vt is equal to, going to be 12, isn't it? No, it's going to be 8. 8. And it's going to be meters per second. And you can kind of get it. If you divide this up into 3 bits, you have 3 bits here and 4 bits there. 3 bits give you 6, 4 bits gives you 8, because it goes linearly.
Ratio?
It's just a ratio, yeah. This is the physics explanation, but it's just going in a ratio. Cool? Okay. So expect something to do with kinematics, angular kinematics, and expect something to do with translation between tangential stuff and angular stuff, something like that. Where are we headed? We're headed to this next bit, which is rotational force or torque. If I ask you to push the door open, and you push the door open near the crack, the door moves quite quickly. If by chance you have something in your right hand, so you push the door open with your left hand, which is near the hinge, how hard is it to push the door open, pushing near the hinge, compared with near the crack? It's much harder. It's the same door, same hinge. How does it know? How does it care? The door is opened by a torque. And a torque is the product of the force you apply and the distance of that force from the turning axis. We intuitively know this. If I'm packing a backpack, my daughter's at a school where I love it because, so I failed the 11 plus, and so I was destined for trade school. I was going to, at my generation, you'd be a pipe fitter, or you'd be a plumber, or you'd be a joiner, or something like that. And the British system had that, academic people went one way, other people went the other way. And I didn't make the cut, so I was going to trade school. But the trade school said, this is a crazy system, so we're going to work people really hard and give them the choice. So they gave me homework that was just like a crazy amount of homework. But I ended up passing enough exams when I was 16 that I could get through back on an academic track. And for me, I don't know. If my house is anything to judge by, I would have been a disaster as anything like, using my hands or stuff like that. It's like, so I saved the world from a whole bunch of leaky pipes and stuff like that. So it's a different skill set, and I just had a different skill set. But my daughter's going to the same kind of school. They just give an awful lot of homework, and I kind of love it. She complains, but I kind of love it. And she has this backpack. She's a little 12-year-old kid, so it's this little 12-year-old kid. And she has this backpack that goes out like that, I swear. She gets out of the car in the morning, and it's like the biggest backpack I've ever seen in my life. And I'm amazed she can lift it sometimes. And what I'm trying to convince her is that there's pockets, and those pockets are really useful. If you had a big, heavy book, where would you put that big, heavy book? Would you put that big, heavy book in the outside pocket so you could get to it easily? Or would you put it in the inside pocket near your shoulders? Inside pocket near your shoulders. If you see my daughter, will you tell her that? Because she goes, I can still carry it. It's just I can get it so much easier from this outside pocket. But yeah, we know these intuitive things about torque. We just don't formally talk about them. So that's what we're going to do now. So here's a generic diagram. Here we have a wrench. And here we have a force that's applied. And the two of them are not in line, and they're not perpendicular at some angle to each other. And it turns out that the torque, the turning force, if you like, is a product of what we call the lever arm and the perpendicular force. So it would be that distance there, the length of the wrench, multiplied by the component of the force that's perpendicular to it. But just as well would be the original force multiplied by the perpendicular distance, the perpendicular lever arm. Any combination, as long as the component of the force you're using is perpendicular to the component of the lever arm that you're using, as long as they're 90 degrees to each other, this works. This is somewhat reminiscent of work. Work was force times distance in its simplest form, and we said work was equal to force dotted with d in its vector form, and we said that was force times d times the cosine of the angle between them. And we needed the force to be in line with the displacement. Remember that perpendicular, no work was done. This is similar but different. For torque, yeah, you can write it down as force times d, but you better be sure what you mean by that. And what we say, this is d crossed with F. And that equals, well, you can write it down as F times d times the sine of the angle between them. So they're not the same, even though this first expression might lead you to think they are the same. They're not the same. And because they're a cross product, two things. The answer is a vector. Now, what on earth is that about? The answer is a vector, and the order of the vector matters. And what you find with vector products is, this is my prejudice, it's not, you know, both the F and the D are important, but my prejudice is the thing that it's about, in this case forces, is always the second bit in the cross product. And in magnetism, we'll get to that. Magnetism is always the back end of the cross product. So if in doubt, put the most important thing last, and you might be right. But better to know the order. Realize the order matters, and make an attempt to learn it. Okay. So let's play with this. So we say determine the torque about the axis. Oh, so here's my turning axis. I've drawn my wrench as a arrow going from the turning axis to where the force is applied. And then I drew my force as a force, and I gave you the angle in between. So you'd say, well, my torque is equal to, and I do recommend you do this, you're going to say d cross F, which equals d times F times the sine of the angle between.
Wait, is it D or R?
It doesn't matter. It doesn't matter. It's just a letter, meaning, distance. But yeah, it's more often used R.
Because in the diagram you have R and D. So.
Yeah, it doesn't matter. It's whichever one. Oh, I see. I'm sorry about that. So what he's pointing out to me here is that I have this distance R and that distance D. And yes, that's for the diagram, but that's not carrying forwards forever. Okay, so I've thrown it away immediately. And
So the
R in the equation itself is not being used?
so when you say the R in the equation itself, which one do you mean?
Like the FR?
So that F and that R, that is that R. Okay? But when I use the generic equation, I might be talking about that R is a length, and it could be talking about that guy, and my angle could be 90 degrees. Okay? So don't get literally tied to R is that letter, and it's always going to be, it's the force times the perpendicular distance. That's what we're after. Okay? Cool. So in this case, I'm saying D, and okay, so F times D times, so there's my F, and this is my D, and there's my angle between in the parlance of this equation. So I would go, that's 3, and that's 7, and then I've got to be careful about my angle here. Which angle does it matter? It actually turns out it doesn't matter, because if I have not 60, but if I choose to put down, what would it be? 120. It turns out that the sine of 60 is the same as the sine of 120, so you can get away with not not knowing the right angle. And that equals times the sine of 60. So then torque is equal to, and oh man, I brought my calculator with me. So what do I check first of all? I check them in degrees because I'm working in degrees. And I go 3 times 7 times the sine of 60. And that equals 18.18. That's what I'm getting. Yep. Call it 18. What would the units be? Newton meters. It's a force. What does that equation say? It's a distance and it's a force. So the units must be a combination of distance and force. Now, you know, we had Newton meters earlier for work and we called it a joule. So would you call this a joule? I would not. Okay, but you know, dimensionally it's the same. Okay. Cool? Yep, question?
If you use 120, would it be cosine? Or like what?
I'm sorry?
How are you seeing the sine or cosine?
Oh, that comes out of the fact that if I want the force times the perpendicular distance, if you look down here, if this is my original length r, and I want, because I'm going to use that force, I want the perpendicular distance, I have to use trig to get this d. And I would say, well, d over r is equal to the sine of that angle. There's my angle. That's why it's a sine. Yep. Now, can I justify why a sine of the angle makes it into a cross product as opposed to a cosine of the angle makes it into a dot product? No, I can't. But you know, that comes out of that sine angle comes out of the geometry of my diagram. Okay. Okay. Let's try this translation again. So we know that F is equal to MA, F net, or sum of the force equal to MA. The sum of my torques equals I alpha. I, ooh, that's a bit new. I is moment of inertia. And it is the angular mass, if you like. It involves mass, but it also involves how close you are to the turning axis in terms of your mass. So let's play with this. So we say a cylinder of radius 3 meters is rotated by a turning axis O by a tangential force of N. Moment of inertia is 6 kilogram meter squared. What is the angular acceleration? So we like to have questions where we have pieces of string wrapped around the outside of a circle because it means that it's, without telling you, it's tangential. But in this case, I tell you it's tangential. That's 7 newtons. Tangent is at 90 degrees to the radius, and the radius is 3 meters. So there's my diagram.
Moment of inertia is measured in kilograms meters squared.
Yep. So that's at 90 degrees to each other. That's nice. So my torque is equal to R cross F, which equals R times F times the sine of the angle between. So torque is equal to 3 times, oh, I'm sorry. What is the angular acceleration? Well, okay, I'll just, I'm doing a different problem here.
Yes, asking about the angular.
I just got that, yeah, sorry. So I can say, okay, let's have a look. What do I have? I have an F is equal to 7 newtons, and I have an R is equal to 3 meters. And I want to find my angular acceleration alpha is equal to I don't know. And then I go, oh, well, what do I do? And I go, oh, yeah, I remember. If F is equal to MA, then torque is equal to I alpha, because I've already got an I as well. I is equal to 6 kilogram meters squared. Oh, I get it. So,
Torque is 7 newtons.
no, we'll get to that. So then I say, well, in that case then, torque is equal to I alpha. My torque is equal to that, which equals 3 times 3 times 7 times the sine of 90, which equals 21 Newton meters. So then I say, okay, 21 is equal to I.
Where are you getting the R from in the equation?
In the equation, I'm getting it from that, which is that. Okay? So then I'm getting 21 is equal to I times alpha, and my I is 6 times alpha is what I want to find out. So alpha is equal to 21 over 6, which equals, what's that going to be, 7 over 2, which equals 3.5, and it will be radians per second squared. So I made a bit of a hash of that because I was answering the wrong question, so let's just recap it. So I did my diagram, and I said, what do I know? And I know that my moment of inertia for this system, for the actual disk, is 6 kilograms per meter, 6 kilogram meter squared. I know the force that I'm applying tangentially is 7 newtons. I know that the radius between where the circular axis is and where the force is applied is 3 meters. That's what counts. I want to find my alpha, and I go, gee, what links these things? And I go, well, I know that F equals ma, so I know that torque is equal to I alpha. I'm not given torque, but I can work out torque from those two guys. So I say, well, torque is equal to F cross R, which equals R times R cross F, which equals R times F times the sine of the angle, which is 3 times 7 times the sine of 90, which is 21. So then I substitute in. 21 is equal to my moment of inertia, which is 6 times alpha. Okay? So agreed? Cool. This raises moments of inertia with us, so we've got to learn a little bit about moments of inertia. This might seem, I remember seeing this and just being completely nonplussed by the fact that mass was seemingly no longer mass. It is. It's just that its inertial effect on angular acceleration depends upon where it is. If I spin and keep my arms in close to myself, as we'll see in lab today, then it's easy for me to start spinning or to stop spinning. If I spin and put my arms out, it's harder for me to start spinning or stop spinning. You can do that in class. And your chairs, just bring your arms in and wiggle from side to side. If you don't do it, you're going to really regret it when you're old, okay? And then try and do the same thing as quick as you can. You put your arms out. And you just cannot do it as fast with your arms out as your arms in. You're just as strong. The only thing is you've moved more of your mass away from your turning axis. In doing that, you have increased your moment of inertia. In doing that, you have made yourself more sluggish in terms of changing your angular velocity. So position is important. And so we take the simplest case to begin with and we say, look, here's a turning axis, here's a mass, it's connected by some piece of string or whatever, something massless that I can ignore. And I say, well, what is my moment of inertia? And I don't derive this, I just present it and say, it is the radius squared times the mass. So if I double the distance between the turning axis and my mass, I really, really make myself sluggish. It's not twice as sluggish, it's 4 times as sluggish. If I triple the distance from the turning axis to my mass, I am 9 times more sluggish. If I'm 4 times the distance, I'm 16 times more sluggish. So it really matters. Okay, and if I have more than one mass at more than one radius, the total effect is the sum of all those things. So that's another little wrinkle. Okay, let's do one of those. I find that I tend to get this a little bit mixed up with center of mass. Moment of inertia and center of mass kind of look similar. So I put them side by side and compare and contrast them so I don't get them confused. Because what I see, the most common mistake in this is people start trying to answer this like it's a centre of mass problem. And that's not what I'm asking here. It says determine the moment of inertia about the origin of the system. So I say, well, my moment of inertia is equal to the sum of each mass's radius squared times each mass. So let's put that in the parlance of this thing. So pick one of these as number one. There's number one. So I'm going to say this is going to equal that distance there. It doesn't actually matter because it's squared, but it doesn't actually matter because I only want the distance. So that would be 3 squared. And the mass
So
times 4.
how we know which one to use?
I'm sorry?
How we know like which numbers to use?
I'm looking at this guy down here. I'm saying, what is its distance from the turning axis? And what is its mass? And I'm using this equation, yeah? Okay. And then pick the next one. And its distance from the turning axis, if you look at your diagram, is only 2. So that would be 2 squared times 5. And then I'm going to look at this guy up here. Oh, man. This is insidious because it's not on an axis. That's the distance I want.
Should we use signs like
You're going to work out this distance, however you're going to work it out. You're going to work it out. And, you know, you could use trig if you knew the angle, or you could use Pythagoras. And I think the easier way is to use Pythagoras, yeah? It's a right triangle. That distance there for the right triangle is 3. That distance there for the right triangle is 4. So what's the distance here?
5.
5, yeah. 3, 4, 5 triangle.
Yeah.
If not, you can work it out. 4 4s are 16, 3 3s are 9, 16 and 9 is 25, square root of 25 is 5. You can do it either way. I mean, it doesn't have to be a 3, 4, 5 triangle, but it makes it a bit easier when you recognize it. So if that is 5, then this means that this is 5 squared times its mass, which is 3. So my moment of inertia is equal to 9 times 4 plus 4 times 5 plus 25 times 3. So my moment of inertia is 3 9s 27, 4 9s are 36, plus 20, plus 75, which equals 95, 131, I think. 131. What would the units be? Look at your equation.
meters per
Kilogram, meters squared. Always look at your equation for your units. So, not bad. It's a little bit long, but not bad. Things that will trip you up are people will sometimes worry about the positive and negative signs, even though it's squared for the distance. People will look at when it's not on axis and they'll not think about Pythagoras, which is, people will sometimes, occasionally people are just not, they're just not practiced, they don't draw diagrams and they don't look at diagrams. And so they'll not get the fact that the 3 kilogram is 4 meters in the y-axis rather than 3 meters, and you know, they just won't interpret the graph well. My wife, who works in, she's in science, her big plea is get people to look at diagrams and draw graphs, because that's where she feels people having a tough time, and I must agree. Ooh, let's say that the mass is so dispersed, or if you like, there's so much of it, that it's not discrete particles at the end of a distance. I mean, so okay. Let's say we had a teacup. And let's say I wanted to know the moment of inertia of this teacup about that axis there. In practical terms, how would I do it? As a physicist, I'd go, it's a trivial example, grow up, who cares, you know? As an engineer, I'd say, actually, this is important. So how would I do it? And I could do it by dividing this up into a million blocks and running that previous equation, I is equal to the sum of r squared m, I could do that for those million blocks. And I'd get my answer. And I'd need a computer to do it, but I'd get my answer. It's kind of like, and that's iterative methods, and they're really powerful. They're great. The problem is when you get something that lends itself to mathematics, to calculus, and you don't do it, you try and use your computer to do that. And I'd like you to know both approaches. When you get into engineering, you're going to get to work with things like MATLAB and the like, and you're going to use computer iteration, and I really strongly advise you to grab it. It's really powerful. And if you become a physics major or a geology major or something, then I would still try and get a copy of MATLAB and play with it and really try and, because it makes it very practical. But don't forget that calculus is still there, and you can use calculus, and you can actually use calculus for some very useful things. And that's what we're going to do. What we say is the moment of inertia as we go to a dispersed mass, a distributed mass, if you like, the moment of inertia about a turning point is equal to, well, it's the sum of ri squared times the little bit of mass as the little bit of mass goes to 0. So it becomes the integral of r squared dm. How long have I got? I've got just enough time. So that's the take-home equation. Now what I do is I know that, and from that by analogy, I can very easily get, why is it r squared dm and not m dr squared? I don't know, that's a math thing. It's r squared dm. So, using the method of calculus that is shown in physics class, that's now, it's also on the web, by the way, show that the moment of inertia of a solid cylinder about the axis through its circular center is a half mr squared. We're using calculus to derive an important equation. So there's my solid cylinder. And the central axis is the axis that goes through like a wagon wheel axis. Now notice if I picked another axis, I would have a different moment of inertia. Everybody's okay on that? Yeah? So how can I do this? And the way I do it is I imagine a slice. Well, we did this before, didn't we? We did this when we did actually the center of mass, and now we're going to do it for this bit.
So we're making 2 slices in
No, I'm taking a sleeve out. Remember how we do this?
It's just hard to see.
Well, I'm drawing the best I can. Okay. So it's a solid cylinder. There's the material all the way through it, and I'm imagining this sleeve, an annular ring, piece of pipe, however you want to imagine it. Now I need some terminology here, so I'm going to say that the actual radius of the whole thing is r, big R. I'm going to say the distance to the slice that I'm interested in is little r. So little r is a variable and big R is a constant. Agreed? The outside radius never changes, but the slice radius changes because I'm going to go from the smallest slice to the outside slice. I'm going to say the mass is big M. I'm going to say this thickness is T. That's, you know, how much of the, how deep it goes. From the front surface to the back surface is T. And then I'm going to say this slice width is dr, a little bit of r. And I think I'm set then. So I'm going to say, okay, my original equation I is equal to the sum of r squared times m, and these are I, And that becomes, it's the integral of r squared dm. Agreed? Yep. Yep. Problem. I don't know how to integrate r squareds with respect to dm. We've been here before, haven't we? Over and over again now. So I say dm is equal to. Now this is a sleeve which has a volume. So I'll get the little volume. Let's not call it that. Let's call it sleeve volume. Times volume density. That's physically what the mass is. That's not a math trick. That's physically what the mass is. So dm is equal to the sleeve volume. And I'm imagining taking that sleeve and pulling it out and then cutting it and unrolling it. So that sleeve becomes a nice wedge. And I know that the thickness is t from the front surface to the back. And I know that the thickness of my slice is dr. What's this distance along here? Can you give me an expression for it? Think about what you did. You took a sleeve and you cut it and unrolled it. 2 pi r. It's the circumference, isn't it? It's the circumference of that sleeve, which is 2 pi r. Okay, so my sleeve volume is going to be dr times 2 pi r times t. That's my sleeve volume, literally. And then this equals the volume density, which is the total mass, divided by the total volume. Ooh, what is the total volume of a cylinder? That's a sphere. Cylinder.
Total volume of a cylinder?
What's the volume of a cylinder?
It's the surface area times 2 times t
Which surface area?
of the face.
It's the circle's area
Yeah.
times the perpendicular height.
Yeah, the surface area of the circle.
So it's going to be pi times, is it little r or big R for this front surface?
Little r. Big r.
It's the cylinder, and the cylinder's dimensions don't change. The sleeve's dimensions change. So it's big R, pi, big R squared, times, what's the depth of this? T. So D is equal to, now we do some cancellations. That cancels with that. So I'm going to say M over big R squared. The T's cancel. 2R dr. Can you double check me on that? Big M's left behind. Big R squared's left behind.
I'm sorry, where are you getting m over pi r squared t?
What's the definition of density?
Mass times volume.
What's the mass?
Mass.
What's the mass on this diagram? Okay. And then the volume is pi big R squared times T. Okay. So I take that guy. And wow, man, this is like the same problem over and over again. I is equal to the integral of r squared dm, which equals the integral of, we've got to leave the r squared there, but I'm just substituting for this dm, so that's going to be, I'm sorry, these should be dm's down here. For some reason my m's didn't come in. M over big R squared, 2R dr. Okay. So I is equal to, let's take out everything that's constant. Well, the mass doesn't change because it's the mass of the cylinder. And the radius of the cylinder doesn't change because it's the radius of the cylinder. And the 2 doesn't change because it's a number. Integral. And it's going to be, oh, r cubed dr. Is that everything? Yeah, r cubed dr. So I is equal to 2m over r squared times r to the 4th over 4, and it goes between the lower limit is 0 because it's the middle, and the outer limit in letter terms is big R, because that's the radius of the outside edge of the cylinder. You don't have any sleeves beyond there. So I is equal to 2m over r squared, big R to the 4th over 4, minus 0 to the 4th over 4. So I is equal to 2m over r squared times big R to the 4th over 4, which equals 1/2 m r squared.
Why is the big M and big R taken out?
They're constants. You always take out the constants from inside your integral. We just derived a really useful equation for moment of inertia. There are three objects that we like to know the moment of inertia for. We like to know it for a solid cylinder. We like to know it for a hollow hoop. And we like to know it for a solid sphere. And this is, so that one is 1/2 m r squared. This hollow hoop is m r squared, and this one is 2/5 m r squared. So, but we just derived this one. I suppose we could derive the others, but it's more complicated, and I'm happy with this, okay? Expect that to be on the test. I got 2 minutes, so I want to just double check. Okay. This is what this says. It's basically, I'm sorry, but I was deciding to be clever, so I put everything over the base 10, which is a total waste of time. Learn that as for a hollow hoop, it's 1. For a solid cylinder, it's 1/2. And for that one, it's 2/5. It's just me being silly. If I do not ask you to use the method of calculus as shown in class, and I say a solid cylinder is that radius and that mass, what's its moment of inertia? You'd simply go solid cylinder, solid cylinder is equal to 1/2 m r squared, which is 1/2 times 2, I'm rushing, I'm sorry, times 4 squared, which equals 16 kilogram meter squared. Okay? So you don't have to always use calculus. I'm going to come back to this bit in a minute.